Earth, our home. Where is it? What is it made of? How has it changed over time? The Earth is just one of several planets that orbit the Sun, which provide the light and heat responsible for sustaining life on Earth. In order from the Sun, the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The Earth itself has several layers that differ in chemical composition and physical properties. The atmosphere, the hydrosphere, the lithosphere, the asthenosphere, the mesosphere, and the outer and inner core. The atmosphere is a mix of gases, mainly nitrogen and oxygen, that extends about 100 kilometers out from the surface and is held there by Earth's gravitational pull. The hydrosphere encompasses all of the water on the planet, including oceans, lakes, rivers, groundwater, water frozen in ice, and even water vapor in the air. The lithosphere is made up of two types of crust. Continental crust is mostly above water and contains considerable amounts of silicon and aluminum, with an average density of 2.7 grams per cubic centimeter. Oceanic crust occurs below the oceans and is composed mostly of dark igneous rocks, basalt, and gabbro. It is more dense than continental crust at 3 grams per cubic centimeter. The asthenosphere, or upper mantle, flows slowly under heat and pressure, providing a relatively soft, weak zone over which the lithosphere may move. Partial melting of the asthenosphere produces magma, some of which rises to the surface as it becomes less dense than the surrounding material. It is thought to be composed mainly of peridotite, a dark, dense, igneous rock containing abundant iron and magnesium. The mesosphere, or lower mantle, is composed of the same rock as the asthenosphere, but is more solid, presumably due to increased pressure that forces atoms into a denser, more rigid structure. The core is the densest part of the Earth, at 10 to 13 grams per cubic centimeter, and occupies 16% of the Earth's total volume. Seismic data indicates that the core has two distinct regions, a solid inner core and a liquid outer core, both thought to consist mostly of iron and a small amount of nickel. The surface of the Earth has its own distinct features. At the bottom of the ocean, there are broad, symmetrical ridges 2 to 3 kilometers higher than the average depth of the seafloor, called mid-ocean ridges. The East Pacific Rise crosses the Pacific and heads towards North America. At the western edge of South America, we see a deep oceanic trench called the Peru-Chile Trench, flanked by a mountain range on the coast. These are the Andes Mountains, the world's longest mountain range on land at 7,000 kilometers in length. On the east coast is the Atlantic Forest. This is a flat area of land called a coastal plain, a low, smooth area adjacent to a seacoast that is separated from the rest of the continent by other features. At the Gulf of Mexico, we can see that the water near the coast is much shallower than in the middle of the Gulf. The continent actually continues out from the coast under the water for several kilometers until it drops off. This submerged bench is known as the continental shelf, the true boundary between continental and oceanic crust. The seawaters have eroded the edge of the continent and risen above it, creating the visible coastlines. The Gulf is surrounded by the Gulf coastal plains, which follow the Mississippi River northward to the Ohio River about 800 kilometers. This continent is bordered on both sides by mountain ranges. Mountain ranges don't always occur at the edges of continents. The Ural Mountains of western Russia and the Himalaya Range at the northern edge of India are good examples. The Himalayas boast the tallest mountains on Earth, Mount Everest, at 8.8 kilometers from sea level. Altitudes higher than 8 kilometers do not have enough oxygen in the atmosphere to sustain human life. We mentioned that the Andes Mountains are the longest mountain range on land, but the longest range on Earth is actually below the Atlantic Ocean. The Mid-Atlantic Ridge is 10,000 kilometers long and connects with other mid-ocean ridges that encircle the globe at the base of every ocean, with the total length of 80,000 kilometers. The island of Iceland is actually part of the Mid-Atlantic Ridge that is extended above sea level. The surface of the Earth has changed during its 4.6 billion year lifespan. Oceans have frozen, dried, and thawed, Mountains have risen and have been worn away by erosion. The continents have moved. If we could bring South America and Africa together at their continental shelves, they would fit perfectly together like puzzle pieces. The fit of continental coastlines and other supporting evidence preserved in rocks and fossils inspired geological theorists to suggest that all of the continents were joined together at one point, but have since drifted apart. This is known as the continental drift theory. In 1912, Alfred Wegener proposed that the landmasses of today originated as part of a single supercontinent called Pangaea, meaning all land in Greek. This has been suggested before, but Wegener was the first to provide extensive evidence from several fields. His investigations revealed that mountain ranges in South America and Africa appeared to line up. So too did strata and coal fields in North America and Europe. Matching fossils, as well as living animals and plants, were found on either side of the ocean as well. However, he was unable to provide a convincing explanation for the physical processes which might have caused this drift. Magma rose beneath the continental crust, causing fractures in volcanic activity. As the crust stretched, a rift valley developed and lava flowed into the valley floor. As the spreading continued, the continent split apart and the valley became flooded. As this movement continued, the continents were pushed further apart, forming the ocean basin and ocean ridge system. Regions where this process of rifting and spreading occurs are called divergent boundaries. Today, the continents continue to push apart and spread through what is known as subduction. Oceanic crust moves like a conveyor belt, forming new crust and recycling the old. Oceanic crusts aren't the only crusts to converge. These two plates, bordered with continental crust, have collided and continue to push against each other today. Neither mass of crust fully subducts, however, because of the great thickness and low density. Instead, both plates press continuously against each other, pushing the mountain elevation higher and higher. Earth's crust moves as the result of two processes. These two plates of oceanic and continental crust move together as one unit.